All right, so today's lecture is about error correction. It's about error correcting codes. Now, this is a lecture that this is a topic that many of you will find quite difficult. Okay? Right. Yeah. Having trouble with the display. So, I'm just going to continue with the lecture, and if you can figure out.
Trying to get your computer.
Right. Okay. So, thanks. So, so now, let me just say a little bit about this lecture and where it sits, and what how many students tend to react to it. So, first of all, what does this lecture do? It's a window into a whole big world about error correcting codes. Error correcting codes. This is a vast subject. Okay, those of you who want to do electrical engineering or work in computer networks, things like that, you'll find that this is a really important subject. It shows up even in architectures in terms of storing data. So it shows up in a number of different fields, and it's a vast subject. Okay, so what if it's a vast subject, why do we bother to teach you 1 or 2 lectures about it? So here's the fact that these 1 or 2 lectures will tell you. Okay, on the one hand, it'll tell you almost everything you need to know about error correcting codes. Okay, so then if it tells you almost everything you need to know, why are there whole courses devoted to it? Because what we'll tell, in this course, what we teach you about error correcting codes is we draw the big picture. Okay, it tells you how it's done, it tells you what it is, and why it should be possible. So first of all, it's not even clear initially that this should be possible. And then it turns out that there are these properties of polynomials which make it possible. So that's a great thing. Okay, now, so then why aren't you done with everything you want to know about error correction? Well, the point is that if you want to actually implement it in practice, the methods that we show you in this class, they are somewhat efficient, but they are not very efficient. Okay? The fact that error correcting codes are used everywhere, so each one of your lives has been touched very deeply by error correcting codes, whether you know it or not, right? Okay, so the fact that this is such a pervasive part of our world, that's made possible by the fact that error correcting codes are extremely efficient. Okay, this kind of efficiency you do not get by the techniques that we'll teach you here. Okay, so but then what's the point studying this thing in this sort of half-assed way? Why are we teaching you this? Okay, well, the point is that this gives you the big picture. Now, those of you who are never those of you who are never again going to study error correcting codes, what this does for you is you now know something very fundamental. Something that's it's something fundamental that touches everybody's lives today. Okay, so it's something that anybody who is educated should know about. Anybody who is educated in computer science, electrical engineering should know about. So that's the first thing. The second thing is, those of you who are going to go and study more about error correction, it does something even more important for you. Because what it does is, going into the course, now you have a canvas with everything sketched on it. Okay, and now when you go and take that course, you have a place to put everything. Right? Everything new that you learn, it's much easier to learn a new subject when you already have a canvas all set up with a sketch of the subject all set up. Because then you can color in little pieces of it. If you don't have that, you get the details, you're missing the big picture, it's just so much harder to do anything with it. Okay, so these are the 2 reasons that we include this subject in this course. There's a third reason. The third reason is it's beautiful. It makes use of these properties of polynomials So when you're doing discrete mathematics, okay, these are, so what we decided at some point is that we were going to, redesign the course. This was a different course once upon a time. We decided to redesign it, and we decided to throw out all those topics. Given that there's so much beautiful discrete math that's available, we decided to throw out anything that's any topic which wasn't beautiful or was not very useful. Okay? And so what we've tried to do is include only those topics which hopefully have both these characteristics. And this particular topic has it in spades. Okay. That said, many of you are going to hate error correcting codes because you won't understand it. Okay. This is not because it's difficult. Okay. But there's a picture that you have to understand. And so what I'll try to do in this lecture is I'll try to show you what this picture is. If you get the picture, it's going to be an easy subject for you. Okay. But it won't be that easy. Right? Because this is trying to do a lot. It's an ambitious lecture. We are trying to cover a subject. We are trying to make sure that you understand this thing, which, well, depending upon which of two camps you are in, if you're going to take much more, if you're going to take more courses on error correction, then it sets you up for that. Okay, that's a pretty ambitious undertaking. All right? So in any case, what I'll try to do today is I'll try to make it as accessible to you as possible under the circumstances. But what it does mean is that you can't just sit back and hope to get it. You've got to be actively involved in this lecture. Okay? But the rewards are great if you are actively involved and if you do understand it. And if you don't, then, well, you're no worse off. You will still have the notes and you can go back and try to make the best you can out of that. I mean, the notes are pretty good. It's just not, there's a one-shot deal here in terms of getting the picture, and hopefully you'll get it. Okay, so any luck?
No, the VGA is working.
Okay. Oh, fantastic! Thanks a lot. Any tips about what I should have done, or is it too complicated to?
Pretty much getting it out by just unplugged it and plugged it back in.
Oh, I see. Okay. Okay, great, thanks. So the problem was on this end and not at that end.
Right.
Okay, great. Thanks.
Have a good class.
All right, thanks. Okay. Okay. So, so as I already said, error correction shows up everywhere. Okay, it shows up in every form of communication. It shows up in media, in video, audio, in any kind of digital media. It also shows up in this was a project at Berkeley in the systems group called the RAPE project. Okay, what does the acronym stand for? Redundant arrays of inexpensive disks. So the idea was that, this was a computer architecture project, okay, which was quite famous. It was a very successful project. And the idea was, if you're storing massive amounts of data, you have a choice. You can use either expensive disks, which are reliable, or you could just use very inexpensive disks, lots of them, so that none of them is very reliable. But then you store your data in a distributed fashion using error correcting codes. Okay? The cloud, that's all about error correction. Okay, so maybe this is a bit dated. Maybe I should have thought about cloud computing, right? Where you take your data, you sort of you scatter it in the cloud. But now, no one node is very reliable. You have your precious data. You've consigned it to the cloud. How do you know you'll ever get it back? Error correction, right? So this is something that's really pervasive. It's ubiquitous, and sort of understanding how it works is really critical in many different areas. Okay, last time we talked about this problem, which is sort of a toy. It's sort of a baby problem in error correction. It's called erasure codes, and there are certain circumstances in which it's appropriate. For example, packet losses on the internet, where you know the identities of the packets. They come with header information, so you know it's the first packet or the second packet you got. You know whether you got them or you didn't get them. And if you got the packet, it was, there was completely fine. There was nothing wrong with it. The only question is, did you get all the packets that were sent to you? Right? So that's called an erasure error, because some of the data that's being transmitted to you got erased along the way. Okay, so today we're going to talk about general errors. So now, instead of packets, we'll think of a message which consists of n characters. So what's a character? Well, a character you might think of as a bit. It could be a character like an English character, an ASCII character. It might be one of 26 possibilities or 30 possibilities, or it might be a byte of data, or it might be, 32 bits long, or it might be something much longer. So that's what we're calling a character. It's a character meaning it's one out of some number of possibilities. Maybe it's one out of 2 raised to the power 32 possibilities, something even larger. Okay, but there are n such blocks of data, each of which we call a character. Okay? Now, these are being transmitted. So we think of, even though the circumstances in which we apply error correcting codes are diverse, okay? So we are storing the data, it's a music file, it's communication. But for the purposes of conceptually thinking about it, we'll think of the data as being transmitted over a wire, right? Just to have an image in mind. And then, as the data is being transmitted, some of it gets corrupted. So now this is much more insidious than erasures, right? So here, all n characters are actually received. There's no problem getting all n characters. The problem is some of them got corrupted along the way. Okay? So you actually got the character, but it may be the wrong character. Now, I claim that this is a much harder problem to deal with than erasures, right? Because in erasures, at least you know where you stand. Okay, if you got the data, you know it's correct. If you didn't get it, you know you're missing that particular piece of data. Here, you don't know. Somebody has changed some of the data from under you. Now, how do you recover? Okay, so the basic idea is still going to be the same. Instead of n characters, we are going to transmit n plus k characters for some k. So we're going to use redundancy. And then, if we get, if sufficiently many of the characters are received uncorrupted, okay, if the number of characters that are corrupted is sufficiently small, then we'll be able to reconstruct all the n characters that were being sent to us. So the message is n characters long. The message was transmitted, but then we had a certain amount of redundancy built in, and as long as we did not too much of the data got corrupted along the way, then we can recover from it perfectly. That's what an error correcting code guarantees. So now there are two important parameters here, right? So one is how much redundancy did you have to use? Right? That's a very important parameter, because we want to do this efficiently. We want k to be small compared to n, right? So we want the redundancy to be something like 10% or 20%. We don't want to take a file of length n, and then instead of n, we don't want to transmit 100 times n or 1,000,000 times n. That would be terrible, right? The second parameter is how many errors can we tolerate? Right? So if we did increase by 10%, but all we could tolerate is 1 error or 2 errors, that's not so good. We want to be able to tolerate a number of errors which is proportional to k. Okay? And so that's going to determine the quality of the error correcting code. And then there's this third parameter associated with error correcting codes, which is how efficiently can you actually reconstruct the data? So what does your reconstruction algorithm look like, and what does the encoding algorithm look like? So these are sort of all the issues that are associated with error correcting codes. Now, what I'd like to do is, before we get to the general picture, I just want to show you a toy error correcting code. Now, the advantage of this is that it's very simple. You'll be able to, it'll be completely transparent to you, hopefully. You'll understand it perfectly. And it has all the characteristics that we want from an error correcting code. Okay? So once you understand that, then I'll show you what a more general error correcting code looks like. And you'll be able to see, and you'll be able to say, oh yeah, okay, I understood that before. This is it's just a little bit more complicated, but it's along the same lines. Right? So what I'd like you to get out of this next thing is the template, what an error correcting code looks like. Okay? All right, and we'll do it by example, because it's not, once you see the example, you'll sort of see how it works in general. Okay, so okay, so let's fix a finite field. So let's fix the field of 7 elements. Okay, so what do we call it? F7 or GF7, whatever it is. So meaning we are working modulo 7. Okay, that's our example. Okay, so let's say our characters are also numbers mod 7. And let's say that we want to transmit exactly 2 characters. So we're going to assume n equal to 2. So we have 2 characters, mod 7. And let's say the first character, C0, was 4. C1 was 3.
Sorry, I don't mind these parts of the
Okay, so okay, so let's draw a picture. Here we have the numbers mod 7, so it's 0, 1, 2, 3, 4, 5, 6. Okay, so what do we want? We want okay, so we want C0 to be 1, 2, 3, 4. So we want that. C1 to be 3. So we want that. Okay. So now, and the way we are going to encode this data is by sort of doing the obvious thing. We are going to pass a line through these 2 points. Okay? And let that line represent the message. Okay, so we are going to identify a message with this line. Okay, so what's a line? Well, it's going to take on value. Sorry, what was this? 4, 3. Oops. What did I do here? Maybe I pushed a bit too. So it was 3. So it was 4, 3, 2, 1, right? So so let's do this. Let's have black for this, 2, 1, 0. How do you extend the straight line now? -1, right? Is 6. 5, -2. Right, that's a straight line. Yeah? Okay. Okay, so now, let's say that we wish to be able to recover from 1 error. Okay, so suppose we want to be able to recover from 1 error. Okay, so So if we want to recover from one error, what we plan to do is we plan to transmit 2 extra points, right? So we were supposed to transmit the first message, which was 4, second message, which was 3, but now instead first character and second character. So this was our message. But now, to add redundancy, we are going to actually transmit 4 characters. This one, this one, this one, and this one. Okay, so our message was 4, 3. What we actually transmit is 4, 3, 2, 1. What do we receive? Well, we don't know, right? Because that depends upon what happens during the transmission, because there's noise in during the transmission. And so one of these characters gets corrupted. Which one? It's up to you. Which one gets corrupted? This one? Sorry. Sorry, anybody, yeah. This one got corrupted, and what was its new value? Okay, so let's say this guy got corrupted, and let's say that what you received instead was 0. 0, okay? Okay, so let's say that you instead got that. So you receive 4, 3. Can you see that? Is that too light? Yeah, okay, so let's, oh my God. Okay, so what you receive is 4, 3, 0, 1. Okay, so now you're sitting at the other end and you're looking at this message, 4, 3, 0, 1. You have no idea which of these 4 places got corrupted. You know that the first 2 were the real message, and the third and the fourth. You talked in advance to the person who is sending it to you, and you decided on the scheme. So you know that if the error did not hit this or this, then you got the message the way it was intended to be. So you could hope that the error actually did not strike one of these 2, as it was in this case. But you don't know, right? I mean, the error could have struck here. How do you know it didn't? Okay? Okay. So now, what can you do? Well, what you know is that the four characters that were sent to you, they lie on a straight line. Okay? So now can you figure out, so the data that you have is that, and that, right? So you've got that point up there, this one, and that one. Okay? So can you pass a straight line through 3 of them? Because you know 3 of them were correct. Is there any way to pass a straight line through 3 of them so that it goes through this one? No, right? So how do we know not? How do we know you cannot do that? Okay, so okay, and this is a crucial part of this whole construction. So if you understand this, then you're more than 50% of the way to understanding general error correction. Okay, so the crucial thing here is, suppose you could pass a straight line through this and 2 of the other points. Okay? Well, you know that those other 2 points were correct. Whichever two you picked, those other 2 were correct. They were uncorrupted because there was only one that was corrupted. But now if you got 2 correct points and you passed a line through them, what do you know about it? It's unique. Right? There's one and only one point line that goes through 2 points. Right? Okay, so but we know one line that went through the 2 correct points. It was the line we started with. So that means that you must have reconstructed the correct line. Does it make sense? Okay, so if you can find any algorithm, any way you want, right, to create a line that goes through 3 of the points, then you've reconstructed the original message. Make sense? Yes.
Does that hold only if your total number of points is 4? Or, you know,
Okay, very, very good question. I was coming to that. So let's do the same thing now. Suppose we want to recover from two errors. Okay, so suppose you want to recover from 2 errors. So now, what we are going to do is we are going to transmit this value, that's the original message. We're going to transmit this one, this one, this one, and this one. Okay, so we're going to transmit twice as many extra points as we did before. Before we transmitted 2, now we're going to transmit 4 extra points in addition to the original message. Okay? Now, we want to recover from 2 errors. So any 2 of these, any 2 points could get corrupted in any way. Right? That's what we are thinking. Any 2 could be corrupted. So which other one would you want corrupted? I'm sorry? You'd like this one first and last being this one. Okay? Well, oops. Okay, so now instead, okay, let's see. So we get some value here. Which one would you like? 2. So that's the new value. And then what would you like out here? 0. Okay. So now, what does the recipient see? So the recipient sees, okay, so what do you transmit? Okay, so let's go through that thing again. So what do you transmit? You transmit 4, 3, 2, 1, 4, 3, 2, 1, 0, 6, right? So we transmitted that many. And then what do you receive? Okay, so you transmit this, the person you're sending it to receives, well, they didn't get 4, they got 2. Oops, sorry. I'm sorry. Okay, you receive 2, 3, 2, 1, 0, and 0, right? And now, again, we're back to the same situation. We're going to claim that if you find any way of okay, so you know that 2 of the points got corrupted, but 4 of the values were correct. You don't know which 4. But you know that there must be a line through all the correct ones. So you know there's a line through 4 of them. Right? So what we know is that there's a line through 4 of the points, of the 6 points. So now we claim, let's try to find a line through 4 of the points, including at least one of the incorrect ones. Okay, so if you include at least one of the incorrect ones, well, maybe you even include both the incorrect ones Now, how many of the correct ones do you have to include if you're going to go through 4 points? Right? There are only 2 incorrect points. Right? If you're going to go through 4, at least 2 of them have to be correct. As soon as you go through 2 correct points, what do you know? There's a unique line, right? Through those 2 points. But we already know of one line through those 2 points. It's the one we originally picked. Does it make sense? So it must be the correct line. Okay? Now, you might be thinking this is very simple, this is too simple. But the whole point about powerful ideas is that they are usually very simple. Okay? So if you do understand it, you should be thrilled. If you don't understand it, you should try to understand it, because you are this close to understanding the whole thing. Yeah? Yeah. So let's try to do a line through. I'm sorry? Yes. So if 0 and 1 both got corrupted, and then? Well, so we have 6 points that we received, right? So we are sitting at the recipient end. We did not know what the person was trying to tell us. We just got these six points. We are trying to figure out, trying our best to figure out what this person could possibly have meant. We know there were errors along the way. So what do? We try to find a line that goes through. We know there are at most 2 errors, so we know that there must be a line through 4 of them. I'm sorry? Well, then tough. Okay, so what all we know is we are hoping that there were at most 2 errors. If everything got corrupted, tough. There's nothing you can do about it. So you've got to make an assumption saying that the number of errors was bounded by a certain amount, right? If the number of errors exceeds a certain amount, maybe you'll be able to correct it, maybe you won't. Right? The guarantee is that if there are at most 2 errors, you'll definitely correct it. Okay? Yes. Sorry. Yes, ma'am.
So I'm kind of confused as to how we went. So we have 2 points, or we've made a line that goes through 4.
Sorry, we made a line that went through these 2. These are the 2 that were our message. We were trying to transmit C0 and C1. C0 was 4, C1 was 3. So we passed a line through that. Okay? And then we said, there are all these extra points that we could transmit. These are the redundant, this is the redundancy we've added. Now, how much of this redundancy should we use? Well, it depends upon how many errors we expect, how many we want to tolerate. If we only want to tolerate 1 error, then it's sufficient for us to use 2 redundant points. That's what we did before. But then we said, let's get more ambitious. Let's try to recover from 2 errors. So now we added more redundancy. It's still the same line. The line was determined by C0 and C1. So now we look at that line and we transmit its value at 0, 1, that's the original message, then 2, 3, 4, 5. This was the redundancy. See, we transmitted these 6 values. The person at the other end did not get these 6 values. They got only 4 of them. The other 2 got corrupted. And which 2 got corrupted? That's the luck of the draw. It's what happened during the transmission. How did it get corrupted? Again, that's the luck of the draw. We know nothing about which ones got corrupted and how they got corrupted. All we know is that at most 2 of them did. There could be 2, 1, or 0.
I'm confused by the recovery part.
Okay, so now what do we do in the recovery? So we are sitting here, we got, we were supposed to get that line, okay? What did we get? We got this value. At 0, we got 2 instead of 4. At 1, we happened to get the right value. At 2, 3, 4, we got the right value. And at 5, we were supposed to get 6, but we got 0. Okay? So now we are trying to figure out which line could that person have meant, right? Because we are trying to recover the message, but we know that there was a line that was passed through the message. So we are thinking, to recover, we are thinking, can we possibly figure out a line that went through these points? Okay, but what do we know? Let's not panic yet. Okay, so there were 6 points. Only 2 got corrupted. So that means that there were 4 points through which the line is still passing. Right? So now we say to ourselves, can we find any line that goes through any 4 of these points? Okay? So we try all possible lines through all possible 4 tuples of points. What could happen? Well, maybe we find no such lines. Well, that's not possible because there is a line. Okay? Because there was a line. It does go through 4 of them. So we can find a line. What's the other thing that could go wrong? Maybe we found too many lines. Maybe we found not only the line that was the original one, we found a different line that the other person did not intend. So now we want to show there cannot be any such line. There's only one line that goes through 4 of these 6 points. How do we know? Well, because out of the 4 points that we choose to put the line through, there can be at most 2 that were corrupted, because there were only 2 points that were corrupted to begin with. So, meaning that the remaining 2 points must be correct. Now the line goes through all 4, so it must go through those 2 which were not corrupted. But there was one and only one line that went through those 2 points. Because it's linear. Meaning that we got the original line. There's no other way we could reconstruct a line. Yes?
Does this mean that we have to create lines for every possible pairing of the points? So we have to test 2, 3, 2, 2, 1?
Yeah, so that's a good question. So I guess you're asking a question, how hard do we have to work to find this line that goes through 4 of the points? And so, okay, so the answer is, well, let's see that, in this particular case of a line, it's actually not that hard, because a line is determined by 2 points, and so we just have to look at all possible pairs, and look at what line that subtends, and see how many of the points lie on that. And we know that there's going to be exactly one of those which is going to succeed. So it's going to take, the number of lines is going to be, well, however many we transmitted. If that was m, it's going to be m choose 2, about m squared. It's not too bad, it's not great. We'll see that you can do a little better. You could do a little better if you really wanted to. But in any case, this is our toy problem, so maybe we won't worry too much about it. It's good enough for our purposes. Yeah? But the important thing here is that there are 2 pieces to the puzzle. The first piece is it even possible to recover in principle? And that's what this, the lineness, this property of lines that they are determined by 2 points, that guarantees it to us. And then there's the second question, the one that you asked, which is a very important one, which says, how quickly can you find it? Because the argument saying that it's unique, that was sort of saying, look at all possible subsets and so on, and that's not efficient. Yeah. Yes?
So the number of columns with respect to number of extra points is twice the count.
Yeah, very good point. Yeah, very good. So you can generalize this, and now you can say, suppose you wanted to recover from k errors. Yeah, so now what you're going to do is you're going to take, you're going to transmit, well, you have your 2 points for the message plus 2k. Okay? Of course, you have to make sure your field is large enough. So you have to make sure 7 is large enough so that it can accommodate 2 plus 2k points. So So you have to make sure that 7 is larger than 2 plus 2k. So, meaning pick a larger prime if you need to. Okay? And then, and then what you'll receive so you'll transmit these points all on the line. What you'll receive is something where you have k errors. At most k errors, right? And now, if they're at most k errors, how many of the points actually lie on the original line? K plus 2. At least k plus 2 lie on the original line. Now we are going to claim if you have any line that, such that k plus 2 of the points that you receive lie on that line, this is the original line that was sent to you. Why? Because, well, at most k of them could be bad points. That means there are at least 2 good points on there. 2 is all you need to reconstruct the line. Yeah? Sorry? Oh yeah, you're getting ahead of us. So, yes. So very, very good. So the question was, what happens if your message consists of not just 2 characters but more characters? How do you deal with that? Yeah, polynomials. Yeah. So, okay. So basically, this problem should have told you everything you need to learn about error correction, except that we now have to generalize to not just lines, but degree 2 polynomials and degree 3 polynomials. But that's not so hard. It'll look a little more complicated, but this is the idea. Okay, does it make sense? So if you understand this picture and if you keep this picture with you, then the rest of it fits into the same framework. It just gets a little bit more complicated, but not that much. How much more complicated? Well, no more complicated than everything you have seen before with polynomials. Right? Since you understood that, you understand where to go from here. Okay, so shall we take a minute?
In this case, I don't see why we have to have n plus k rather than just have n plus 1 plus k. Because if we know that k are errors, right, and in this case, like if 2 are errors, but we had 3 points, and as long as there are n plus 1 points.
Well, let's see.
Wouldn't there only be one line that went through those?
No, because you're saying suppose there were 1, 2, 3, 4, 5, right? It's n, you're saying 2 plus k plus 1, n plus k plus 1, n is 2, to k plus 1. So k is the number of faults.
Yeah.
So now imagine that this and this were errors, so instead they came here and here. So now, so you have 3 that are on the line. Yeah? So all the errors could conspire to be on a line with something else.
Right.
because you have no control over those.
Yeah.
So the errors, they count in two places. One in how good they make other lines which are not correct,
Right.
but they also count towards making the actual line bad because they go away from the actual line.
Right.
So k gets subtracted from the actual line, and it gets added to the spurious line, and that's why you get a 2k effect. Yeah. Okay, so remember, at least for this segment of the class, there's this one mantra we keep repeating to ourselves over and over again, which is, that a non-zero polynomial of degree d has at most d roots, and that we can interpolate a polynomial of degree d uniquely from d plus 1 points, right? And so this is all we need to know in order to generalize what we were doing earlier completely to what? Well, so remember there we had a message which consisted of 2 characters. Once you have 2 characters, we pass a line through it, and then everything works out. In general, we won't have only 2 characters. Our message might be longer. It might have n characters. And then what do? Well, we do exactly this. We take our n characters, we pass a polynomial of degree n minus 1 through it, and then we evaluate it at more points. That's a redundancy. What we are transmitting is, instead of a line now, we are transmitting this polynomial of degree n minus 1. Okay? And instead of transmitting just n points, we are transmitting more than n points. And then if there are errors, we'll recover from it. So it's completely analogous to what we did already. It's just polynomials instead of linear lines. Lines are degree 1 polynomials. We'll just generalize and make them higher degree polynomials. Okay? So here's what the general picture is. So we transmit the message is n characters long. What we're going to do is we're going to transmit n plus 2k characters, and we'll be able to recover from any k characters being corrupted. So it just generalizes what we said before. Instead of a message of size 2, it's now a message of size n. Instead of lines, it's going to be polynomials of degree n minus 1. Everything else will be the same. Okay? So we're going to, let's see if we can make all that clear. Yes?
Is 2k a strict bound for the amount of extra characters?
Yes. This is a tight bound. So this is actually quite beautiful because it's exactly the right answer. You cannot recover from any less. If you use any less redundancy, then you cannot recover from it. So it's necessary and sufficient.
What if I had 2 characters and there were 2 errors and I transmitted 3 extra points?
Yeah, then you can't recover from that in general. Yeah? Yes?
Why not?
Oh,
Because the number of correct points is still greater than the number of incorrect points.
no, because, well, if you use the line example, right, so if you have two correct points, and then you transmit 3 more, right? So if you have 2 errors, then they're only, on your original line, there are only 3 points. Now, what about, is there any other line you can find? Well, these 2 points that were incorrect could be anywhere. you can make sure that they are collinear with one of your original points, one of the correct points. So now you have a new line which consists of two of the old points and one of the old points and two of the corrupted points. Okay, so let me just sketch it out for you. It's exactly analogous. So what does the picture look like? Well, the picture, let's say we were working mod 7, so we are working mod 7. So we have 0, 1, 2, 3, 4, 5, 6, 0, 1. Okay, and then say our message now. So our message was C0, C1, C2. There were three, n was 3. So we had 3-character long message. Okay? So whatever it was, maybe C0 was 3, C1 was 1, C2 was 4. Okay, so you have a message like that. We can't pass a line through that. But of course we can pass a degree 2 polynomial through that. So what we do is we find a degree 2 polynomial. We know there's exactly one of those, right? So it's going to be of the form P of x is ax squared plus bx plus c. We can solve for this polynomial. You can either use these Lagrange interpolation with these delta functions, or you can write linear equations, right? Because we know the value of this point at 0, 1, and 2. Once you know what x is, right, so it's a polynomial, meaning x has a high power. But if you substitute for x, that high power goes away, right? It's just a constant. So then what do you get left with? So you get P of 0, you substitute x equal to 0, and you get c equal to 3. P of 1 is what? Well, you substitute x equal to 1. So x's go away, and you just get a times 1 plus b times 1 plus c equal to 1. P of 2, again, the x's go away. It's a times 2 squared. So it's 4 times a plus 2 times b plus c equal to 4. You can solve these equations, right? And you can get ABC. So c is already 3. You know a plus b is equal to whatever, it's minus 2. Say we are still working mod 7, right? That's what we are working. 4a plus 2b is 4 minus c, 3. It's 1. This is 5. Okay. So you can solve this, right? You know how to solve this. You multiply this by 2, you subtract from that, etc. Okay, so we figure out this polynomial. Now that we know what this polynomial is, well, we don't want to really figure it out, right? Let's just pretend we know it. Yeah? So now that we know what it is, we can plot out what it looks at at all the other points. So, so maybe it bounces around, maybe it goes, this is what it is at 3, and then maybe it's that at that's the value at 4, and that's the value at 5, and that's the value at 6. Okay, so now we know all its values at all these different points. What do we do? Let's say we want to recover from 2 errors. Instead of just transmitting these 3 points, we'll transmit 4 other points. Luckily, we have exactly 4 other points, so we don't have to expand the field to being even larger. 7 is good enough. So we'll transmit all these 4 points. Now what happens? Well, 2 of them get corrupted. Okay, so 2 of them got corrupted. Maybe this one got corrupted, and in its place we got that point. Maybe that got corrupted, and we got that point. Okay? All right, so now we are sitting at the other end. We received this transmission, and we got, well, at 0 the value is 3, at 1 the value is 1, 2 the value is 2, 3 it's 6, 4 it's 4, 5 it's 5, 6 it's 2. Okay, so we look at this, and then we say, what could that person possibly have been thinking about? We say, let's try to reconstruct a polynomial of degree 2 that goes through these points. Well, we can't. How about trying to find one that goes through most of these points? Well, there are 7 points here. There were 2 errors at most. So we should be able to find a polynomial of degree 2 that goes through 5 of these points. Okay? We know that we can find one such polynomial. Why? Because the original one works. Let's see. Can we now say that we couldn't possibly find a different one? There's no other polynomial of degree 2 that goes through 5 of these points. How do we know? Yeah, because polynomial of degree 2 is defined uniquely by 3 points. Right? Interpolation formula. Right? Property 2 of polynomials. This is one of our mantras. Okay, so so how do we know that if we have a polynomial that goes through 5 of these points, it must go through at least 3 points which are uncorrupted? Well, because there are only 2 points that were corrupted. Right? So out of the 5, at most 2 are corrupted, so there are 3 that must be correct. Yeah? You take a polynomial of degree 2 through these 3 correct points, there's only one of them. We know that there was one that the person who was transmitting the data was thinking of, so that must be the one that we figured out. And so we've recovered the data. Yeah? Okay, so this works in complete generality, right? A message with n characters, you put a polynomial of degree n minus 1 through it, you extend, you now take 2k redundant points, you transmit the whole thing, ship it across, you have k errors, the person at the other end, if they can figure out how to pass a polynomial through n plus k of the received points, okay, then they have reconstructed the original polynomial. They can evaluate the original polynomial at these first n points. They recovered the original message. Okay, that's error correction, that's all it is. Okay? It's an absolutely beautiful idea. It's very simple, it's very powerful, right? And much of the digital world would be impossible without this today. Yeah.
So understand that if you take 5 points, you guarantee 3 correct points. 3 points will give you polynomial degree 2. My question is, what happens if you do grab 5 of which 2 are wrong? How do you know which 3 are the correct ones?
Oh, you mean how do you actually reconstruct the polynomial?
Yeah.
What I'm claiming is that, well, okay. So what I'm actually telling you is that if you have a polynomial of degree 2 that goes through 5 points, then none of those 5 points can be incorrect, right? Because we know that there's a unique polynomial of degree 2 that goes through those 5 points, but the unique polynomial of degree 2 that goes through that 5 points is the one that we originally picked. And that goes through, everything it goes through is the correct point.
So do you just try all the different sets of 5 and whichever one gives you an actual polynomial degree 2 that works?
Yeah, that would not be very efficient. Yeah? So there has to be another chapter to this story which says, how do you do this efficiently, right? But so far, all we want to know is that this scheme actually works, that it has the right properties. That if you could possibly implement this, then you would get the correct, then you'd have reconstructed the data, right? A priori, we had no reason to suspect that we should be able to do this. I mean, this is, this was a huge, this was a major sort of realization. There was no reason we should have been so lucky. Yeah? Okay. Okay, so now let me tell you how we actually compute this polynomial. Okay, and so the way we compute this is by using what's called the Welch-Berlekamp algorithm. Berlekamp, he was a professor in the math department here. Well, actually, he was also the first chair of the computer science department, but long ago when computer science was a part of mathematics. Maybe you didn't know this. Okay? So at Berkeley, computer science was once sat inside the math department, and then it moved. Okay? And so I think he's now Professor Emeritus. He might be a university professor. He actually came up with this algorithm, and together with his collaborator Welch. And instead of publishing it, they actually patented it. So where it was sitting was in a patent application. I had a student back in the 90s, Madhusudan, who, he was taking a course on coding theory. He sort of figured out that there was this patent. He went and looked at the patent. You couldn't read this patent. You had to really work at trying to understand the algorithm. And he sort of read through and figured it out, and then wrote it up. And it's a beautiful algorithm. Once you extract it and you understand it, it's a really beautiful algorithm. Okay, and so okay. So let me tell you what this algorithm actually looks like. So today, this is, it's been used in many places in coding theory, in this connection between coding theory and computer science. It's used in many places on that interface. So how does this algorithm work? Okay, so let's see. Maybe. Oh, I don't want to do that. So let's draw it again. Okay, so. Okay, let's. Maybe I'll try to fit it in here. Let's see if it works. If not, okay. So here's our setup. We have this polynomial p of x. It's of degree 2, whatever degree it happens to be, right? It's of degree n minus 1. So we have our polynomial p of x. This is our original polynomial. Okay. Now, we are transmitting p of x. We are transmitting its value at n plus 2k points. And then we have k errors. So in our case, k equal to 2, n equal to 3. Right? Okay. So I'm just going to go through the example, but everything works sort of in the same way. So now, at the receiving end, you do not get p of x. You get r of x. R of x is equal to p of x, except at the green points, where it's the green value. Right? R of x is equal to the received value. Okay? The problem is there are errors. Right? So how do we given R of x, how do we actually solve for the coefficients of P of x? Right? It seems sort of impossible. So there's this very beautiful idea that Berlekamp-Welch had, which is that of an error locator polynomial. So the error locator polynomial is 0 at all those points x where P of x is not equal to R of x. So it just tells you where the errors occurred. It's 0 at those points, exactly those points where errors occurred. So which are the 2 points where errors occurred? It's x equal to 2 and x equal to 5. So what degree polynomial do you need to make sure that it is 0 at these 2 points? Degree 2, right? There are 2 roots. So what should the polynomial look like? X minus 2 times x minus 5. I'm sorry? No. So now we are playing God, right? We know what the situation is. We are just trying to develop the theory, and then we'll go back and apply an algorithm. Okay, so right now we are just looking down on the entire situation and figuring out how to proceed. Okay? So there's this error locator polynomial, which we'll call E. Oh, sorry, you cannot see this. Equal to E of x. Okay, so remember, there's the polynomial P of x. There's a non-polynomial. This is the received values, R of x. And then there's this error locator polynomial E of x, which is 0 at exactly those points, those values x, where an error occurred. So it's x minus 2 times x minus 5. We don't happen to, when we actually receive the message, we do not know that 2 and 5 were the errors, but it's some polynomial of degree exactly equal to k. K is 2. So now what can we say? What we can say is that P of x times E of x is equal to R of x times E of x. This is true for all x, regardless of whether an error occurred or not. Is this clear? If an error occurred, then these two sides are equal, even though R of x is not equal to P of x, because we are multiplying both sides by 0. So everything's fine. If there's no error, then we have no idea what the error locator polynomial is, but it's the same thing on both sides. And P of x equal to R of x as well, so left-hand side equal to right-hand side. So in both cases, left-hand side, regardless of what x is, whether it's an error or not, this always holds. Okay. So now, what do we know? This, let's call this equal to q of x. What's the degree of q of x? Well, it's the degree of P of x plus the degree of, so the degree is the degree of P of x plus the degree of E of x. What was the degree of P of x? It was n, right? Oh, sorry, you're right. It's n minus 1. What's the degree of E of x? It's k. So you have n minus 1 plus k. This is an n minus 1 plus k degree polynomial. Okay? What's the degree of E of x? It's k, right? But even though it has degree k, the number of quantities we do not know about this polynomial is actually k minus 1, because we know the highest degree term is x to the k. There's no coefficient in front, right? Because it's x minus something times x minus something times x minus something. So what's the highest power of x? It's x to the k without a coefficient. The coefficient is 1. So if you want to know how many unknowns there are exactly k minus 1 unknowns. Right? What about r of x? Who's going to figure out r of x? This is what we are receiving, right? This is the corrupted message we are getting. So r of x is known at each of these points. Q of x is unknown. E of x is unknown. So what do? We write out a system of linear equations. One for each value of x. How many values of x do we have? N plus 2k. N plus 2k? We have n plus 2k equations. Right? So we have this many equations. Right? N plus 2k equations. How many unknowns do we have? Well, for this, we have degree plus 1, right? Because 1 for each degree, and then there's a constant term as well. So it's degree plus 1. So we get n minus 1 plus k plus 1, which is n plus k. How many do we get from here? From E of x. How many unknowns? K. So we have n plus k, which is n plus 2k unknowns. You have n plus 2k unknowns. You have n plus 2k equations. You solve. You live happily ever after because you can solve those n plus 2k equations. So what do you figure out in the process? So what did we figure out? Well, we figured out q of x and e of x. So if you know q of x and e of x, well, q of x is p of x times e of x. So if you know this and you know e of x, what do? You just divide and you figure out p of x. Okay? It's, if you think about it, it's actually not that complicated. It's actually quite simple. Right? But it's absolutely brilliant. Okay?